The math club today ought to be a pretty good one. Um, So another kind of a fun one. It's actually how to use mathematics to make certain patterns and designs, using some algebra and some geometry, stuff that all of you have seen in at least some small sense. So if you want to break the elements, there will be pizza, and it should be a fun, very accessible talk. Okay, questions? All right, so what we're going to do today is we're going to talk about inner products. Now I'm going to introduce something called the dot product of two vectors. It's a way to multiply two vectors together and you get a number out. There's a more general thing. A dot product is a special case of something called an inner product. And we'll talk about this more generally as this unfolds. So how many of you have heard of the dot product? How many of you are in Cal 3 and just living the dream with the dot product, right? I mean, so that's where you encounter it most. It's got some geometric things. So for those of you this will be a little bit familiar, and if not, it shouldn't matter anyway. How many of you have seen more general inner product, maybe using integrals? Yes, you will. So the dot product play multiply vectors together. Now, let me just kind of get right to it and tell you what it is. Definition. But using the so these are just two brackets, right? And we'll write actually, let me bring this to what I was doing. Now, if you think about this carefully, can anybody think of a way to multiply this using what we know, right? This is what an n by 1 matrix and an n by 1 matrix. Can you multiply those? You can't really multiply those matrices unless n equals 1, right? Which is very silly. But you can manipulate this a little bit. This is an n by 1 matrix, and this is an n by 1 matrix, correct? And I did promise you that I'm going to tell you when to multiply two vectors and get a number. What is a number as a matrix? What size is that? It's a 1 by 1. So could you think, okay, yeah, this is n by 1, n by 1. It doesn't quite work, but how could I manipulate this and get a 1 by 1 matrix? if this were 1 by n, I'd be good to go. Everybody agree with that? But it's not, so I can do the transpose. When I take the transpose of this is 1 by n, comes in by 1, and this is an element in element. And so notice dot product. This is just the number that is U1 B1 plus U2 B2. Anybody have these? So for example, this is pretty easy to answer. If I have 1049 Q and say B is -2113, then U dot B is U transpose times B, which is of course, once you get going on this, basically you just kind of match them up and multiply and add. So that's going to be -2 plus 0 plus 4 plus 27, which is 20. Okay. So that's how the dot product works. Let me ask you this. This is a number, right? So you can think about this as a one by one matrix. What is so what we got is for this particular example. One by one matrix. What's the transpose? 29. Transpose of that is it's just 29, right? Here's just one by one matrix. What's the transpose of this? This is D transpose times U transpose transpose. That's my first observation. Order of the dot product doesn't matter. You can do it either way and you get the same answer. That's good. This is not true for matrices in general, but when I do a dot product, when I do that kind of multiplication, then you're good. So let's record some properties of dot product. By the way, when you if you look at the dot products here, this is -13 -8 plus 21. See, it turns out that that number that you get to do the dot product encodes information about the expected. In fact, it's probably not clear at all, except in the fact that the dot product. These two vectors, if you were drawn in free space, are at right angles to each other. Right? And that's because dot product is 0. We're going to see why that's true in a moment. But see, drawing this, trying to figure out and getting out my protractor and acting like I'm in geometry and trying to measure its 90-degree angle, that's not so easy. So the dot product immediately tells me these things sit at right angles. And we'll see why that's true in a moment. But let's begin with some basic properties of the dot product. Theorem. Let U, B, and W in R and C and so C is just a number. then, U dot V is V dot V. We've already seen this, doesn't matter what order you do it in. V if I add two vectors and dot them with W, then this is you can distribute that W through. Boy, that's what I would hope happen in this case here. C, if I take a constant times the vector U and dot it with W, this is equal to U dot with same constant times W, which is C so in other words, you can slot a constant anywhere you want. The dot product, you can pull it out of the first, out of the second, out of the like. Huh. What happens when you dot a vector with a cell? Well, before I write this answer down, let's kind of do an experiment over here and see how to figure this out. Let's say, just for giggles, that U is the column vector U1, U2, UN. And U dotted with cell is U1 squared plus U2 squared. UN squared. Everybody agree with that? And so there's one thing that I can say about it. Can anybody make an observation about that? So when I dot a vector with myself, I get this number, which is what I get when I add up n squared. What must be true of this number if I'm adding up n squared? That is correct. This is a number, and it's greater than or equal to 0. Right? Here we're assuming everybody else did. And let's suppose, just for the sake of argument, that this thing actually is 0. What does that tell you about every one of these UIs? They all have to be 0. Otherwise, you're hosed. Because if any of these things is not 0, then you're going to have a piece that's at least a little bit positive, right? And so the only way you get 0 is if all the entries are 0. So U dot U is 0 if and only if U is the 0 vector. Right? This last one was kind of an important observation because this last one, see, whenever you dot a vector with a cell, you get a non-negative number. And in fact, you get 0 if and only if the vector that you input here is the 0 vector. This actually gives us a tool that allows us to define length. And the length that we get is what you would expect, the old Pythagorean. Yes.
Why does it actually greater your amount? How does it never end up being negative?
Because
Oh wait, never mind. Sorry.
you okay with that? Because
Yeah.
everything's square.
Yeah, but I didn't realize.
Okay, so property D allows us to find the length. can actually do complex vectors too, but I'm not going to talk about that just yet. Need to do some stuff with complex computation. Definition. Let's suppose that V is in Rn. We define the length, or sometimes I'll say the norm of V by, it's sort of like an absolute value symbol, right? Absolute value sort of measures the size of the number. It's like an absolute value symbol, so it's got two brackets here. This is just V done. Actually, square. So if V so the length of V is just the square root of the sum of the squares of all its components. This is exactly, I mean, this is basically Pythagoras, right? The measures length. So let me just do for two vector. So for example, suppose I have the vector AB, right? And it means the tip of my arrow is at the point AB, correct? And so if I were to draw a picture of this, then this length here is B, and this length here is A. Agree? Now notice that my length formula in this case, the length of U is the square root of A squared plus B squared, which is exactly the length of this hypotenuse here, right? So this is good old fashioned, all-American, makes sense kind of thing, right? Because it's just really Pythagoras theorem. By the way, you might complain a little bit that, oh, well, Jim, you only did an example for a two-dimensional vector. What if you had something like B is equal to vector 2, 2, 1? Then the length of B is now you can actually draw this and do Pythagoras' theorem twice and figure it out, but this really doesn't matter. This is generalizable because notice that any vector, I don't care how many coordinates they have 50 million coordinates, every vector lies in some plane. And really what you're doing is Pythagoras' theorem. Okay. Any questions? Yes.
Can you take the dot product or something that is a by one vector?
No, it's only defined for vectors so far, right? So when I talk about a dot product or an inner product, I'm only talking about vectors. Okay. Let me make a couple of notes here. Suppose we have vector B in Rn and C a real number. Then, if you look at the length, anybody want to guess what this is? How does the relate? How does the relation between the length of C times B and the length of C itself? How do you suppose it relate? Yeah,
Oh, you just multiply it by C.
almost. What if C is negative? So what you said is correct in spirit. Can you update it? What's up?
Oh, you have to take the absolute value of it.
And we can see this rather directly because B is B1, B2, Bn. And CB is CB1, CB2, CBN. And if you look at the length of CBN, CD, that is. This is the square root of C1, CB1 squared plus CB2 squared. CBN squared. Now notice there's a factor of C squared in there. And this, well, this piece right here is the length of theta. And this piece here, the square root of C squared, is the absolute values. Any questions? And let me make one more definition. If any of you have seen Cal 3, or if any of you have taken a physics class, especially like a dynamics class or statics class, you probably, how many of you have ever heard the term unit vector? Right, this is going to come up if it hasn't for you already in some of your engineering or science classes. But sometimes vectors, they're out of control, right? They're too big, or they're pointing the wrong direction, or something like this, or they're too small sometimes. And so sometimes what you want to do is you want to normalize your vector. Right, so you've got all these vectors that you're needing in the problem, but they're kind of a mixed bag because this one has length 2, and this one has length 4, and this one has length 27, and you want to kind of get them all uniform. So definition. Let U, sounds like B, be a non-zero. And you'll see in a moment why demand is non-zero. But if you look at this vector here, is a vector in the same direction as V. Right, with length 1. And it is called the unit vector. Right. Okay. So really, we're going to be using unit vectors a lot to sort of uniformize calculations later, but there's really nothing to this. What you do is you take whatever V is. If it's too long, you squeeze it down to 1. If it's too short, you expand it to 1. Let me talk you through this a little bit. Notice that 1 over the length of V, well, that's just a number. right? So that means that U is a multiple of V, and so it points in the same direction, plus or minus. But this thing that I'm multiplying by is always positive, right? Because the length of V is a positive number. So it's definitely in the same direction. And notice that the length of U is the length of 1 over by our previous result. This is the absolute value of 1 over the length of V times the length of V. But the absolute value of a positive number is positive. So the length of U is exact. So we've scaled it to like that. Okay, any questions? Let me think of something. I'm not having a stroke here. It might seem like a non sequitur, but your exam before it takes place right before Thanksgiving on Monday, right? So Monday night's kind of out for a review session, and I suppose that I'm gonna run into trouble the weekend. I would strongly suggest, so y'all look at your schedules, we're gonna do a recap in class on Friday, of course, when we follow up, but I would suggest we do a review session Thursday night of next week. Is anybody gonna have a serious problem? Yes.
If there's a physics exam at 7.
No, that is. Well, how long is your physics exam?
Usually about an hour.
Like 7 to 8. It's like 7 to 8.
Yeah.
Okay, I'll keep that in mind. I mean, what time do you want to be there?
Well, it's online, it's usually just a ring. You do it wherever. So I can browser.
Oh, you can just do it wherever. So we'll have a physics party. All right, so I'll keep that in mind. And we'll, yeah, 7 to 8. We could do it Friday night, but I suspect that would probably go against the grain of some here. I couldn't start till probably about at least 6:30, so. Anyway, y'all think about that, and I'll check on that for the next week. Yeah, and of course, I could actually do a review session earlier on Thursday. I could do it. Well, I could do it as soon as I can get a room. How many do you have classes at 5? On Thursday? 5 till 5:30 until. How about 4? Plus 4 on Thursday? Okay, you guys think what you said. All right. So, okay, I want to talk about distance vectors. The first thing I'm going to do is I'm going to remind you, how many of you have seen the law of cosines before? Right, at some point in the past, you've probably all seen that in a trig class or something like that. If you want a proof of that, I'll be happy to do one in my office. I don't think I have time for this. But I mean, basically, if you believe the Pythagorean theorem, which is actually easy to prove, if you believe the Pythagorean theorem, then the law of cosines follows from this. So here's what it says. If you have a triangle like this, and theta is the angle opposite C, law of cosines. Then C squared and C squared is A squared plus B squared minus 2AB cosine theta. Notice if theta is a 90-degree angle, what kind of triangle is this? It's a right triangle. And if theta is a 90-degree angle, this piece goes away because cosine of power 2 is 0, right? And we get Pythagoras theorem back. And actually, if you know Pythagoras theorem, you can prove the law of cosines fairly easily. By the way, there is actually a proof of Pythagorean theorem in the old mathematical literature that was written by a former president of the United States. Does anybody know the president? James Garfield actually published proof of Pythagoras theorem. And they killed him for it. So anyway, be careful with math. So this is the law of cosine. I'm going to use this. But first I'm going to define the distance between two vectors. Now, these vectors can be very large, right? They can be in 100,000 dimensional space. It doesn't matter because two vectors are either on the same line or they define a plane. Everybody agree with that? So if you got two vectors, I don't care how many dimensions you are, those two vectors just by themselves define a two-dimensional subspace, which is a plane, right? So there's no loss of generality in me writing this picture. Let's call this U and P. And this vector right here is, well, actually, it doesn't matter which way I put the arrow. This is this vector here is U minus P. Do I agree with that? It's because V, so this one on top plus the yellow is equal to U. Everybody agree with that? This is when we have vectors head and tail. We define the distance between U and P you would does it this way. I will sometimes just call it D for distance between V. This is just the length of the yellow side. Everybody agree with that? This is what we're calling the distance between these vectors. Just measure the difference between their heads, which is U minus V. And let me point out that this is symmetric. The difference between the vector U minus V and V minus U is instead of putting the arrowhead here, you put it here. It's got the same length. Everybody agree with that? So this is the way we find the distance between two vectors. And from this, I'm going to derive some interesting ways to, well, I'm going to derive some stuff that the dot product actually tells you about the relationship between these two vectors. So let me do the law of cosine. Let's go back to the law of cosine. The distance between U and V is this thing right here, right? So let me point out that if I call this, if I rename this C and A and B, then I'm going to use the law of cosines. Now, let me recouch this in terms of the garbage we learned today. And what is C squared? It is this distance, it's the yellow distance, the length of that square, which is U minus V dotted with itself. Everybody agree with me? It's this vector, u minus v, dotted with itself. That gives you the square of its length, right? And I'm gonna do the same thing for this other garbage. What is a squared? Well, it's u dotted with itself, which is length of u squared. That way, b is length v squared. 2 length of u, length of v. Everybody okay? So it's just a reimagining of law of cosines. This thing is u dot v dotted with itself. This is u dotted with itself, which is the length of u squared. This is v dotted with itself, which is the length of v squared. And then 2a is the length of u, v is the length of v cosine. Now, let me massage this a little bit by kind of working out the left side of that equation. So if you look at u dot v on the left side, this is u dot u minus u dot v minus v dot u plus v dot v equals the length of u squared plus the length of v squared minus 2 length of u length of v goes on that. Same little things. Everybody okay with it? Now, right. Notice these two terms are the same, because remember, order of dot product doesn't matter. U dot v and v dot u are the same thing. Everybody good with that? And notice this is the length of u square. This is the length of v square. I've got two of these things. Equals the length of u squared plus the length of v squared minus 2 length of u length of v. And notice that there's some serious cancellation, right? These two disappear. These two disappear, leaving a much more modest formula. And now, in fact, I can divide out by -2. And I get this very fundamental formula. This means that the product that we computed is not just some kind of crazy number that we did just for the sake of it. There's a lot of information encoded in this, because when you get that dot product, what that is that's the length of the first vector times the length of the second vector times the cosine of the angle between those two vectors, which is really super, really cool. So, for example, find the angle between, let me mix it up. 1, 0, minus 1, 1, and 2, 3, 1, minus 2. I mean, good luck drawing this at all, right? These are two vectors in 4-dimensional space, right? I don't really have a good feeling for that. There's no way I can draw it. But I can tell you that if you just look at those two vectors that define that plane, exactly what the angle between them is. And this is absolutely fascinating. This is beyond my capability really to draw well, but I can figure this out absolutely. So here, let's give them names. We'll call this U and this V. Notice that the length of U is the square root of 1 plus 0 plus 1 plus 1. So I get radical 3. The length of V is the square root of 4 plus 9 plus 1 plus 9, which is 20 square root of 23. And U dot V, well, see, that's going to be 2 plus 0 minus 1 minus 3, which is negative 2. So, what is the angle between them? Cosine theta is U dot V over the length of U times the length of V, which in this case is negative 2 over the square root of 69. So what can you say about this? So here's the angle. It's whatever that is, but here's one thing that I can tell you. The angle between these two vectors. Well, what can you say about it? It's bigger than 90 degrees. If I agree with that, because the inverse cosine, that's a negative number, so the inverse cosine returns something in the whatever quadrant, right? And let's see, that's a little bit less than 1/4. Radical 69 is a little bit bigger than 8, right? So it's not going to be too much more than 90 degrees, but it's going to be an open 90 degrees. Your calculator can give that to you. Long. Any questions on it? This is amazing, right? You can draw this, but nonetheless, you can figure out what this is. Let me give you a couple of nice offshoots of this. What's the definition first? Definition. We say U and well, let me say this. But U and V, we vectors in Rn. We say U and V are orthogonal. And I think orthogonal was invented as a column for the perpendicular. It just means they sit at right angles. That's all it is. Or orthogonal. Sometimes we might even write it this way. This is kind of a common shortcut. U is orthogonal to V. If the angle between them that is, they sit at right angles to each other, if you like. And let me also give you kind of a caveat, you might wonder about it. We're going to assume that the zero vector is orthogonal to every vector, right? Because I mean, it kind of doesn't have an angle itself, but that'll just make things convenient. Theorem. Fantastic. This is a wonderful theorem because this is a quick, actually orthogonal vectors are incredibly important because one of the things that we're going to do kind of toward the end game in this class is we're going to look at orthogonal bases. They're very convenient. They allow you to do things. They allow you to make computations easier. You want to check oftentimes the two things are orthogonal because maybe you want to make bases out of them. So that's these two parts. Here's a quick check, super dot product. And you can't expect something much more quick than that. Computing a dot product is a very quick thing to do. And if and only if you get zero, then they're orthogonal. And the proof of this, how we've developed it, it's easy. And again, we're assuming that U and V are not zero, because otherwise we've got problems here. And we did give you the caveat that all we're going to assume that zero vectors are orthogonal to everything. Notice that if theta is pi over 2, then cosine of theta is 0, which implies U dot V is 0. Right, because if this side is 0, then that is 0. And on the other hand, if U dot V equals 0, then cosine theta is 0, and so they set at right angles. Yes,
Why is it only pi over 2 and not like 3 pi over 2 or?
because the inverse cosine function only returns values between 0 and pi. So yeah, I mean, you can recalibrate it if you want, but you can always assume it's between 0 and pi. Let me give you a follow-up theorem to this. This one I won't bother to prove because this is just basically the Pythagorean. But I think it's what. So let me finish up with just a couple of things. I'm going to give you a definition first. Suppose V inside Rn is a substance. So I've got Rn and I've got some subspace, like maybe some column space for matrix or something like that. We define B, see that little X or that little exponent is a perpendicular sign. This is sometimes called V perp. This is the collection of all W and Rn such that W is perpendicular to V for all V. So what you do is you look at everything that's perpendicular to every vector in V, including the 0 vector. And this is called is the orthogonal complex. And it is a subspace. As a matter of fact, notice, let me point out that in the special case that if you look at a couple of special cases, if V consists only of 0 vector, then V perp is everything, because everything is perpendicular to 0 vector. And on the other hand, the other extreme case, if V is all of Rn, then V perp is only the 0 vector. But if you have some subspace, then it's perfect. Actually, we're gonna see some problems. Let me give you a last theorem here, that I'll let you cogitate. But, hey. And, let me point out that the proof of this is really almost by definition, but I'll let you think about this. Let A be an invite matrix. Anybody want to guess what the orthogonal complement to the row space is? It's everything that kills all the row. Yeah. It's not, as a matter of fact, and if you think about that, I think you'll kind of figure that out. And the curve of the column space is the null space of the dimensional space. Once you know this, and I know this, we know relationship on the rows. Okay, any questions? All right, that's a good place to quit. Are there any questions? Think about coming to math club this afternoon. Otherwise, you guys have a good weekend.